Um, Hello, everyone, and welcome to today's webinar. Um, as everyone can see my screen. If not, please drop me something in the question area. So let's get started. So today we will have a very important topic. We will talk about SOLIDWORKS Flow Simulation, and we have a case study from our customer in Spain, and what the customer is doing is traveling to the space using a new technique, and this new technique is a Bloostar. They invented a new way to go to space. So uh, what they are doing, they are using SolidWorks uh, CAD and SolidWorks Flow Simulation. The company name is Zero to Infinity, and as I said, they had the inflated balloon and ascending to the airspace, avoiding, of course, the complex of the ignition from the ground, and then they stop and then release the balloon, release the Bloostar, the rocket. So it's already above the air, and it does not require that launch efficiency. Uh, so they really simplify the access to the space from anywhere, anytime. So really, they changed the game, um, and of course, they can hold a good volume and even a good weight and Bloostar. Then it started to release some of the engines after releasing from the balloon, and it's still a green environment. So because it's already releasing all the gases, the helium outside uh, in the airspace. So until it reached the orbit required. So let's summarize that um, into stages. So what they actually did is um, it's a three-stage rocket that is designed to put into orbit satellite with a maximum weight of 100 kilogram and a volume of 2.4 cubic meter. And the cost actually is around $4 million. So what makes it different from another companies that the zero to infinity they use a rocket launcher from the planes, so is that the use of stratospheric balloons as the first stage, and then um, we are here and after that 20 kilometer, and then starting to release the rocket from the balloon until it reached almost the 80 kilometers, and then it started from to release some of the engines. So in a brief, the first phase of the flight is the balloon ascent to near space. So this is from 20 kilometer to 25, lasting around 2 hours. And the second phase of the flight starts. So the second phase actually from 20 to 80. Um, and once the rocket is released from the balloon shortly uh, thereafter, all the 13 engines are ignited. The first stage burns for 100, almost 100 seconds, upon which the vehicle reaches the altitude of 80 kilometers. And actually, will be our main focus and our main study. So what we here to study, what we need to study today is we can split it into three categories. First, we will do the pre-processing, which is the preparation of the simulations, which will be an external flow, and then we will study the results. We look at the results, which we call it the post-processing phase in this case. And then we will include a simulation of the flow of the internal flow inside one of the engines. So during the next 30 minutes, actually, I'm going to show you the basic functionality of SOLIDWORKS Flow Simulation on external flow and analyzing the results even in internal flow. And hopefully that you will gain of the basic capabilities and applications of SOLIDWORKS Flow Simulation through this webinar. So starting from the preparation, we have some assumptions here. We are studying from the first stage, which is the altitude of 25,000 meters. And my assumption is the temperature there is minus 60 degree, and the pressure will be at 2,000 Pascal, and the final speed at this stage will be 2,300 meter per second. So we want to simulate the aerodynamics behavior of the spacecraft at the end of the first stage again. Here's the engine have been working for almost 20 minutes accelerating. So let's get into the analysis. As we can see here, we have the rocket, the Bloostar inside SolidWorks, and we can see basically all the geometry as assembly, which contains the engines, the body of the rocket, everything. And it's being designed in SolidWorks. So how can we move to SolidWorks Flow Simulation? It's easy because it's inside the same interface. Once you have the add-in of SolidWorks Flow Simulation, you will find Flow Simulation Command Manager. And me personally, I'm always find it easier to go with the wizard rather than the manual option. So moving through the wizards, we can decide identify the project name, the comments. For example, we are calculating here the first stage, at the end actually of the first stage. So in this stage, we will see next what will be the unit system. So maybe I'm comfortable with all the unit system except the temperature. So whatever we can change the temperature to be Celsius temperature. And of course, you can change all the parameter over there, but I just make it simple. And here in the wizard, we have to identify whether it will be internal or external flow. And of course, it will be excluding the cavities without the flow conditions. And if there is a gravity, by somehow, we have to identify where is the component of the gravity and what's the gravity magnitude. And next, we need to define the fluid. So in here, for example, we can have a list of material in the library, and of course, we can define new material in the library. So here I'm just defining the air, and of course, I'm expecting the air to be laminate and turbulent as well. So I don't know exactly whether it's going to be laminate or turbulent, so I will just assign that. In the next, in the wizard, we have to identify the thermodynamics parameter, which is accordingly to be the pressure and temperature. In this case, I'm assuming that the pressure will be 2,000 Pascal. And here is the trick. We need to identify where is the location, the axis of and the direction of the velocity. So in this case, I'm defining that in the negative direction of the y-axis, which is the 2.3 kilometer per second. That's the initial parameters. And of course, if we have more to identify the turbulent percentage, we can do that. So once we've done that, SolidWorks Flow Simulation has been created a new project with a complete tree that we can go through all the parameters again. So for example, if we right click, go to the journal settings, we can review all the parameters that we have put previously. And another thing, what we can see clearly that the computational domain, which will allow us to change uh, our domain according to the size we required. Of course, we didn't need uh, in this example to analyze all the universe, so we have to uh, uh, make it smaller a little bit. We can define exactly which size we need of the computational domain. And this is a good thing because really, as long as we are simplifying our problems in the first stage, and as much as we are preparing our model in a good stage, that will give us a accurate result as long as it will be faster than ever. So if I keep it a very big domain, this will just consume me a very long time. However, in this case, I do not need that much big, especially that I don't have any other things in the environments in the domain. Look into the mesh. So we finished with um, the initial conditions with the general settings. And now we have to look at the mesh, which is very important in the pre-processing phase. So we can have settings of different mesh from coarse to fine. Initially, we just started that analysis, and the goal from the analysis here is only to look at the behavior of the flow. So in this case, I don't need that much refining in the mesh. However, the capabilities of SolidWorks flow simulation and the meshing is great because even we can have a local mesh. So after the first phase of analysis, we can enhance our mesh if we need to look at certain areas. And then once we hit run, we can have the analysis that use all our capacity or our computer CPUs, or maybe you need to define it in a special CPUs. And the geometry preparation, that's the window that you can see uh, uh, the processing. So we have just finished the pre-processing, and currently we are in the processing phase. In the processing phase, there is a very good um, indications of the results. So we're still in the iteration 23, for example, and we can look at the results. Some of the results, for example, the number of travels. So how many times the flow will travel, what will be, how long times it will take the flow to travel. At any time, you can stop and play again um, uh, the processing, the results, and also you can plot a very good option here in SolidWorks Flow Simulation that you can plot the results while the iterations of the results is being in process, the calculations result is being in process. And the benefit from doing that is to have initial indications of the results. So you can look initially whether are you converging to the right results, or maybe no, you have just put something wrong in your parameters and you need to redefine it. So after looking to completing the analysis, we will go back to the result. However, what we have seen so far is um, the preparation results, and we have seen how easily we can use SolidWorks Flow Simulation because it's already in a known environment of SolidWorks, and actually we have taken around 5 to 6 minutes to identify the preparation parameter to prepare our model, which is a very short time. Let's move to the next stage, which is the result. So after completing the run, and we need to look at the results. And we have a lot of options here to look at the results. So moving to the result, we can have a mesh, cut plot, isosurface, volume parameter, look at the surface parameter. Of course, I will not be able to show them all. Maybe I will try to concentrate only in the cut plots and the surface plot and the flow trajectories in this example. So first, let's go to the cut plot. And for example, we need to plot the pressure or temperature. So we can plot that according to the type of the plot. So we can go to the velocity, maybe the velocity in X or in Y or in Z, and we have a better understanding of what will be the velocity. Maybe here it will be all in the same color, and I will show you that why in the minutes, because the velocity could be plotted according to the minimum, maximum, or maybe to a certain value, a user-defined value. So here I just let the SolidWorks Flow Simulation to define what will be the minimum maximum value according to the legend. And of course, I can change the level of the gradient. So how many levels do you need to see your colors accordingly? And that's it. We finish with the velocity. Just click OK and you will get it. However, we still have something missing here. Maybe we need to change from velocity to temperature. Maybe need to change it to the pressure. We can do that directly from the legend. But again, we have something missing. If you look at the area here, we are expecting a turbulent flow. So in this case, we need to maybe have another plot showing the velocity and another plot showing the pressure. Moving to the cut plot, and we need to have a better understanding of what will be the streamline of the flow particles. So in here, yes, we can understand where is going to be the turbulent flow. And of course, we can change that, the streamline type, from arrows to lines. We can change the spacing. We can change the size. So all these options are giving more flexibility as a tool of SolidWorks Flow Simulation to give you a better understanding where is going to be the problem. Maybe it's not a problem. Maybe it's a cavitation, for example. So in a different example, we can determine from that the cavitation problem, just like in pumps and casing. So we need to copy the velocity, and we need to make another plot, another cut plot. And to do that, we are using clone. So the clone is one of the good option in SolidWorks Flow Simulation, just to copy a cut plot and maybe change the other one from temperature to pressure. So, or maybe I need to plot the vectors, not the streamlines. So currently I'm plotting the vectors and changing the spacing between the vectors, changing the number of vectors. And here we go. So we can see here all the areas located in the trajectories. Actually, we are showing arrows here, not a complete trajectories. The trajectories, we'll show them later. So we get to go. We almost having the parameter of the velocity, but with a different one. One of good option as well is to show the mesh. Where is the mesh will be located as defined mesh or maybe adaptive mesh? I mean refined mesh. And also we can change the offset, and one of the good options that we can animate the offset distance later on. So we can use SolidWorks motion in plotting the animation of SolidWorks Flow Simulation. However, another block we need to see it now is the pressure that all the faces, the outer faces of our Bloostar, our rocket, has handled. And to do that, I'm using all the faces, and I need to plot the pressures. Once I'm clicking OK, SolidWorks Flow Simulation, what's been done is to show the pressure on the craft. So the spacecraft, the rocket, has been handling a lot of pressure here, and this is the maximum number of pressure according to my assumptions. which is good actually. We can take these results. This is another benefit from using SolidWorks Flow Simulation, is to enhance the result directly from the pressure and take it into SolidWorks static analysis, which will use SolidWorks simulation. Perfect. And another type of result actually is to probe. So for example, if I'm interested to a certain area, I can probe and have only the pressure on this certain area. Let's look at another way of plotting our results, and I will use the flow trajectories because we need to animate exactly the flow. This is the things that we cannot understand, and actually we cannot see the air is moving, but with using SolidWorks Flow Simulation we can do that. So we can specify a starting plane with an offset, of course. So I'm starting the plane 3 meter from the top plane. And we can change the appearance, whether it's going to be pipe, lines, could be an arrows, trajectories, and we can plot different type of plots. As we stated, we can have it at velocity, we can have it at pressure, we can have a temperature. So by this way, we can look at the pipes moving. So maybe we can change a lot of parameters. However, one of the good parameters that we can change is to crop the region. So for example, I'm not interested to have the flow trajectories all over the domain. However, I need just to show that in a certain area, which is in the front of the rocket directly. And to do that, we are cropping the region of the domain to get a better understanding exactly where is going to be the flow, how will the flow behavior will go through the rocket in the area of the front of the rocket. Again, we can change a lot of parameters, changing the number of trajectories, changing the spacing, changing even the transparency of the flow trajectories. So just to save time, I will show you here 2 flow trajectories that I have done previously. One of them is the lines with arrows. So we can just play the animations on the fly to understand the behavior of the flow. And maybe another one we can see clearly, which is the arrows. So let's hide this one and let's show the arrows. So this will give a better understanding through the animation. If we animate that, let's animate it. What will be the velocity distribution along the rocket? So it's endless, actually. It's endless possibilities. So you can change a lot of parameters to have a better look of the behavior of the flow over your rocket. So and here we have seen in the aerodynamic simulation, we have seen the capability of the ease of use the graphic result analysis. So we just focus on maybe 1 or 2 of them, maybe 3 of them. However, we still have a lot of capabilities inside each one of them. So we finished the external flow, and then let's move to the internal flow. And we're going to see how to perform an internal flow analysis. An example, we will use one of the engines from Bloostar. So what we have here is the 7-engine stage, and we will take one of them to perform the analysis. But something we have to understand is that the Bloostar is powered by liquid oxygen and liquid methane, and this is the engine actually. and we can open that engine in a separate window just to understand what's going on. So this is the combination is the perfect match between the performance and simplicity of combustion and green energy. So the engine are optimized to work efficiently in a very low pressure environment, where ignition takes place between 20 to 25 kilometers. So we have to do some simplification here, because in our case, maybe we are not we do not interested to see all the engine geometry. So what we're going to do is to simulate the engine. So I'll just keep it as inlet and outlet. And my problem, actually, just describe it. It's the Bloostar first stage contains 6 engines with a vacuum thrust of 15 Newton. Then the second stage has another 6 engines with 2 kilonewton of vacuum thrust. So we have a total of 13 engines are ignited upon launch from the balloon platform, resulting in a total thrust of 104 kilonewtons. So we need to simulate that. We need to simulate what will be the pressure, the velocity, and of course we do have maybe a supersonic situation. So we need to understand the Mach number. What will be the Mach number all over the body of the engine? So let's go ahead and use the wizard to have a new project, and I'll use the SI meter kilogram in seconds, and of course in here we have to define it as internal flow, and you may go with the external or not, but the most important thing is the gravity, because as we are oriented the engine, the gravity actually should go through the Z component, not the Y component. So according to my assumptions, I will have actually minus 30 meter per second square of the gravity. Another problem we are facing here is the fluid itself. So I have a combination of 2 types of liquids, which is the CO2 and the steam. So can we do that in flow simulation? Yes, we can. So through the flow simulation, we can add multiple fluids. So it's a mixer fluid, or even we can have a subdomain of the flow. Back to the initial conditions, and we need to specify the initial condition as a temperature, and maybe I'm assuming the temperature to be 1000 degree in here, and the pressure will be 10 bar. We get to go, and we can see the computational domain, and maybe we need to identify the goals. We need to identify the boundary condition, which is the inlet flow rate, and also the pressure outside. But with the run here, with the internal flow, we can see clearly the adaptive mesh, which is through the result, through the iterations, what SOLIDWORKS Flow Simulation is trying to do, and even we can have here more than 1000 iterations. So in my case here, because I'm expecting a supersonic situation in the flow, so I'm having the iteration more than maybe 1000. It will not take even much time to resolve it, maybe 30 minutes or something. However, the good thing about the SOLIDWORKS Flow Simulation is that it's showing you the adaptive mesh. So it's as long as going through the iteration, SOLIDWORKS Flow Simulation is trying to optimize the mesh to get the best and the better results. And here we are plotting the Mach number just to understand, are we converging to the right number or not? And look into the results. We can have a cut plot of the results, of course, for the pressure, the Mach number, and the velocities. And how can I do that, for example, in the Mach? Is it required engineering goal like an equation goal. No, in SolidWorks Flow Simulation, you can just plot the Mac directly. And here I plotted the Mac in ISO line um, plot so we can understand what type of, so for example, in near to the body, I'm having a 9 number of Mac. So let's hide that and let's move to another type of result, which is the XY plot. So for example, I need to plot, so here I'm just showing you that we can plot from the pressure to the Mach number directly. You don't have to generate any equations. Let's hide that. And maybe we can go to the XY plot because I need to plot some diagrams, very simple diagrams that show the pressure, velocity, and the Mach number, and maybe the density. So I need to plot them along the length of the engine. So along the length of the engine, I need to see what's the variation, what's the value is different from um, um, one from 0, for example, to whatever the length of the engine. So we can show that, and even we can show that on the screen and scale it. So we can see directly a live indication of the value of the density of the mixture of the CO2 and the steam inside the engine, going from a high density, for example, to low density. Also, we can have this plot exported to Excel, and all the values will be exported to Excel, not only the charts, also the plot data. So you can represent that the way you like it in Excel. Actually, we have different ways of presenting the file outside SolidWorks Flow Simulation. One of them is Excel. The other one is, of course, using animation. And maybe the last one is using e-drawing. So using e-drawing, you can plot your values directly. So what we have seen so far is the rocket engine simulation. And from here, the big value was the automatic mission, actually, in my opinion. Yes, we can plot a lot of results. However, we have seen the adaptive mesh as long as we are going through the analysis. SolidWorks Flow Simulation is helping us on automatic meshing. So I believe that's the end of my webinar today. And through the webinar, we have seen the known environment, the short preparation time, the easy graphic result analysis, and the automatic meshing. Thank you so much for attending today, and please do not hesitate to contact me. That's my email, and of course, if you have any question, please drop your question to your nearest value-added reseller. I believe I have a question here. Do you have any question? So I'm still having, if you like, for 5 and 10 seconds. If you have any question, please let me know. Drop it in the question area. I can see one question here. What's the difference between second and third domain? So yeah, very good question. So I'm having a question here because one of the user maybe is asking, in the meshing we have two type of meshing, 2D and 3D. Of course, by default, The flow simulation is a 3D meshing. However, in some cases, when you have a symmetry in your parameters, you can specify a two-dimension mesh. And not only that, in initial stage, when you just need to understand what will be the behavior of the flow, and you didn't need to spend much time in the processing phase. So in this case, we can advise you to go with the two-dimension just to indicate what will be the result in this case. However, if you find that from your initial parameter that everything is fine, you can go directly with the 3D meshing. Hopefully that this answered the questions. Okay, yeah, we can have a discussion if you are interested. I will revert back to this type of information. So to see what type of information can we share it with you. Okay, very good. Is there any other questions? Thank you all. Thank you very much for attending today, and see you soon in the next webinar. Next week, we will talk about the photorealism and how can we render using SOLIDWORKS Visualize. Thank you and have a good day.